Okay, now the record is on. So let's say I'm going to use this because if you know how to handle this, this will be just the same, but you have only one side of it. Okay, this will be too much even for writing, so I'm not gonna dive into it. So let us take a look at this. Try to write as big as I can. Okay. So let's say this frame has two, not a straight line, but I can actually, oops, keep it like that, and then it's going to turn to a straight line. Okay, so let's say this is your angle alpha. This is your angle beta. Okay, now we know that we have to turn the psi into the delta term to reduce the unknown. So let us assume that this frame goes in this direction. Okay. So it has to be perpendicular to maintain the rigid joint. That's the reason why we draw perpendicular, okay? Because your joint is rigid. And this has to be perpendicular as well, coming out that. And to maintain the delta, now we know that this is delta. And therefore, this is also delta, okay? So we're clear with that. Please let me know immediately if you need more time to write something or to draw something, okay? Because I'm actually pretty quick with the drawing. Okay. So to complete the deflected shape, you have something like that, okay? So now we're gonna look at this. So I am going to put an emphasis on this location. Okay. Now at that location, let's say you have a member here. Okay. And that is your alpha. All right. So because of the fact that we know it's just going to go perpendicular like that. What you need is this. How do you call this color? It's like a pink rose pink, whatever. You need this, right? Because if you have this, it will give you the psi, right? Because the psi is this distance divided by the length of the member. So you will need this. But instead, you have this. Okay, so now you need to turn this delta into the pink distance. Okay, so let's say, how am I going to use this sign convention? Let's say I can call this perhaps, let's call the vertical distance y. And the distance that we need is, let's call it z. Okay, so now when you look at this, you see we have a little triangle here. You see that? And perhaps I should put the y somewhere closer, but anyway, if this is delta, this is also delta, correct? I'm sorry, alpha. If this is alpha, that is alpha. Am I correct? So you can now write that, say, delta over z. Maybe if I should write z with this color, it'd be better. What is that? Delta over c is what? Can you tell me? It's equal. That sounds like you're wrong. Like,
B.
it's sine, right? It's this divided by that. Z is this. We want Z, right? So this is Z, the pink one. That is Z. Okay, so it's sine, right? Sine alpha. So now you can, when you have Z, now you have the so Z, which is the distance that you will use to write this, because let me put it. This is your psi, right? So the psi is simply this Z divided by the length. Now you know the Z, it should be simple enough. Okay? And now let's move on to this member. So it's going to be same, you know, but let me try to find a different color. Maybe this guy. So in similar fashion with the green dotted rectangle, now I have this member, second one, and I have this as beta. And I want this distance, which I should call it C prime, just to differentiate that from the one we had before. Okay. And let's say I can call this one Y prime. Okay. And again, if that is my beta, this is my beta. Correct? And now because we know that this is also the same delta. So now it's again, if you look at this triangle, it's delta over Z again, that is equal to sine theta, right? So it's delta over C prime, which is equal to sine beta. And therefore your C prime here is delta over sine beta. Okay, just a little bit of trigonometry, you know. Another last one. Now keep in mind that we have this member that has a psi term, and the second member here also has the psi term. Okay, the psi doesn't represent the deflected shape, you know, it's just the angle that your member rotates. So you should see that, you know, the top member now move as well. And now because it goes up on this side and it comes down on the other side. So that means for this particular member, this side, let me this side here, it is going to be equal to, you see, y plus y prime over the length. Okay, so that means I am going to have to go ahead and try to derive the y and y prime here as well. And say, now when you look at y and must be represented in terms of delta, right? Because we want to use delta, just our only unknown. So what's going to be? Y, it's going to be delta over y. Now it is equal to 10 alpha. Okay, so you have y equal to delta over 10 alpha. And likewise, here you're going to have your y prime equal to delta over 10 beta. So yeah, just for knowledge, you know. So now you know. Okay. Now the key is to be able to sketch the deflected shape. And when you see the deflected shape, you can have the relationship. And this can measure your love of trigonometry as well. Okay, so any question about this? You know, when I used to give this as an exam, so I cannot say no, it won't be in there, but say it's if I'm going to give you a problem like this in the exam, I must make sure that, you know, I can complete everything within 1 hour. And this kind of thing takes time to do. So it's really not a good idea to try to measure whether or not you can do stuff like this. Okay. Sorry. Question about this? See more. Yeah. Oops. That's better. Used to be part of my class, and you know, a long time ago. Okay. If there is any question, let me begin the new method now. It is what we call the. You guys ready? Question? I'm going to count 1, 2, 3. 1, 2, 3. No question then. So let us see here. Now this is another method. It is completely based on the slope deflection, but you can see a problem like the last example that we had. It could give you a terrible headache to try to solve the equilibrium equations like this. You know, we have 4 equilibrium equations. So right now you can just turn on the computer or the calculator. Your calculator can do it up to 3 by 3 only. And that's my intention, not to give you a problem bigger than that. Okay. But in the old times, the structures of, you know, that they built, they had always been very, very complicated. So in the real world, you're not going to end up with just 4 simultaneous equations or stuff like that. You always have more. You have a very long continuous beam, like 10 spans or something like that, maybe. So it was quite a struggle to try to solve these simultaneous equations. So then came Professor Hardy-Cross. You know, every time I mentioned his method, he, of course, now you know that he was the one who invented this moment distribution method. So Ajahn Ane used to tell me that he was under pressure to put some to make some publication for the university. So one day he went back and he came up with a new method that was very, very popular, because you see that it is very, very quick and useful, especially when you want to approximate the structure in a very short time. It's way quicker than computer. So it was very popular. See, very popular for almost 3 decades until the emergence of the computer. So I think it's extremely useful. And that's why I'm still happy to teach this stuff. Okay, so let's say now the concept for the procedure is this. So we're gonna move back and forth between, I can draw something around here maybe. Okay, so let's say I have a structure like this. Anytime, anywhere, we look at this joint E. Okay, to maybe you can have a joint like that, a joint like that, and maybe you can have a joint like that, maybe you can have a joint like that. So now from moment distribution, if I put the load back here, you would know that at E, there would be moment due to this load and due to the rotation of joint E, correct? So in moment distribution, I say, well, we are going to go ahead and calculate ME, but by doing that, it means we are going to try to lock the joint E, fix or lock the joint. If I say I lock joint E, so that means joint E doesn't have any rotation, I could easily calculate the fixed end moment, correct? Because as I said in the beginning, joint E would have moment due to the load and due to the rotation. So if I lock joint E doesn't have rotation. Moment at E becomes this fixed end moment. Correct? So now we have the moment, but in reality, joint E is not locked in the real world. It has rotation. So once you lock the joint to calculate fixed end moment, you have to release it back to its original form. So upon releasing, when you look at the joint, this fixed end moment now comes out, right? You lock it, so it rotates now. Its fixed end moment comes out like this. Cause the joint to become unbalanced. Okay, so with the, we don't do anything more than equilibrium. So we have to maintain equilibrium. Okay, by this. The members that form the joint will try to bring equilibrium back on the table. So it will have the moment occurring to balance the whole thing. Okay, now the first question that you must answer is, how can we tell how much this moment? So clearly, you can see from this free body diagram that these moments come from the 4 members. So the major contribution is the members. So how are we going to know how much each member will contribute in balancing this moment? Is the answer, is the question you need to answer. Okay, but when you have this stuff, okay, to maintain the equilibrium, away from this, you need to have this moment, so that at this particular point, everything is also balanced. Okay. Now, when you have this moment, another effect that will occur is that when I look at this member, this one, when you have this moment here, surely this will cause the moment on the opposite end as well. So how much of the effect that this moment, which comes from the balance here at the joint, will cause the moment at the opposite end is another question that we have to answer. So, okay, this moment is carried over from this. So this is the moment that we call carryover moment. Okay, how much each member will help contribute balancing the moment here will be determined by the factor that we call distribution factor. Okay, so by knowing these two things, we will be able to use this method to solve for the moment in the indeterminate structure without ever having to come up with those equilibrium equations. Okay, a question about this? Okay, so let's talk about carryover. All right, actually all the answers are here, you know. So you want me to rewrite everything? Just go ahead with this just to save some time. Okay, anyway, because we're talking about the rotation at the joint, so we are saying that the opposite end is going to be fixed, right? We don't care about what kind of joint we have on the opposite end. We are now focusing on the fact that now we have the moment here, how much it's going to be carried over to this side without considering the rotation. But yes, we have rotation here. So from slope deflection, you can write Mij, which is this moment. So it's 2ei over L, 2 zeta I plus zeta j minus 3 psi. We don't care about the rotation here, so we're just going to say it's fixed. Okay, so that means you can say zeta j is 0, and we don't talk about the joint displacement, so let's skip that. And because we talk about the moment here, how much is going to be carried over to this side, so we're not focusing on any load on the structure as well. So fixed end moment is also 0. So now from this, you have Mij is in fact equal to 4ei delta over L. And in similar fashion, I can write Mji. And Mji becomes 2ei zeta I over L. Because now, you know, Mji, zeta j is 0, and you have 1 zeta I as a term here. Okay, so it's 4ei over 4ei zeta I over L and 2ei zeta I over L. So now you can say that Mji is half of Mij. If you cannot recall, you can go back to our examples where, you know, in slope deflection, where you have no load on the structure, you see that your opposite end moment is always a half. For example, do I have a good example here? No, it's just rotation is a bit complicated, but no, I don't have it. Okay, that's too complicated maybe. Okay, let's forget about it. But that's the way it's supposed to be. But oh, this is different stiffness. Anyway, let's forget about that. But I'll find the better examples. Okay, ooh, sorry. So it is Mji is always half of Mij. Okay, that guy has such size way term so that it's not equal. Okay, but if you have a case like this, it's always a half. So we can conclude that the carryover factor is a half. That means if you have Mij here at this joint, automatically the moment on the opposite end is half of that due to this relationship. You see how useful this slope deflection is? So now we can conclude that the carryover factor is a half. If you have 2 here, the moment here is 1. If you have 4 here, that is 2. Okay. The next one is distribution factor. Now I don't have anything here, so it's better now. So let's say now we are going to find out how much each member will contribute to this. So now we have a rigid joint. Okay, so what we can do is now we can assume that zeta EA rigid joint it means that this is E, okay? So let's give it some name, maybe A, B, C, D. Zeta EA must be equal to zeta EB, zeta EC, and zeta ED, because they all rotate at the same angle, right? Now, from the slope deflection equation that we have before, let me scroll back up here. You see, that's the typical equation you're going to have. Please look at that. You see, that's M equal to 4EI over L, and then zeta. So this term, you know, that is stiffness. That relates moment to rotation, because I can also write this equation as M equal to K delta, right? Just like F equal to Kx. So that K, this is the stiffness, the typical stiffness that you will be used to in the future. Okay, so that it's 4EI over L. So from here, I can write that zeta EA basically is going to be equal to M EA L over 4EI, right? If I write in terms of rotation, just a little bit of manipulation, okay? Move L and 4EI on the opposite side, okay? Move L here, and then 4EI becomes the denominator, okay? So now I can have that. And the other reason that why I write it in that fashion is because I can now show you that this L over I is, you know, something that we can call the stiffness, right? It's because when we write the relative stiffness, we always look at the L over I over L term. Okay, that belongs to member EA. And in similar fashion, I can now write the rotation for every member. Okay, so I can now say that MEA over 4E, because we always talk about the stiffness in terms of I over L. So let me put the L down there so I can write I over L. Okay, of member EA now should be equal to MEB over 4E I over L of member EB. And I can go on with MEC over 4E I over L of member EC. And for the last one, let's complete it. ED 4E I over L of member ED. Okay. Now, we all know one thing, that is our sigma ME must be equal to 0. Correct? So because that's because, right? Because sigma ME equal to 0, I can say that my MEA plus MEB plus MEC plus MED, and whatever I have as a sum of fixed moment over there, summation of FEM of joint E, they must come down to 0. Okay. Now, do we have? Yeah, I have more space. So let's call 4EI over L, you know that term. Let's call 4EI over L stiffness. Okay. Now I can write MEB in terms of MEA. Can I? You can look at this. Now I can write MEB here in terms of MEA because I have this proportion. So that means, can I, if I erase, if I reduce the size, will it be better? But, oh, that's not good. But I can write MEB in terms of MEA. So if I call this K, it becomes, this whole term becomes KEB, right? This whole term becomes KEA. So MEB, I can write it as KEB over KEA multiplied by MEA. And likewise, MEC would become KEC over KEA MEA. So when I put this back into my moment equation here, now what do you think I have? Now, skip this. Therefore, I can say MEA. It's MEA, right? Plus MEB here. But I will now write MEB in terms of MEA. So it's KEB over KEA MEA now. And MEC, it's going to be KEC over KEA multiplied by MEA. And the last one is, of course, going to be KEB over KEA MEA. So let's try to write things in the similar term. I can simply add KEA over KEA in front of this, right? It's the same thing. And this is going to be equal to the, let me try to modify things a little bit here. Let's say because the summation here must add this up equal to 0. So if I change this into a negative sign, it's better. So the whole thing must be equal to summation of fixed end moment at E. Okay. So now you know we have this term up front. Just too small, right? So I can rearrange the term. And now it becomes, I can call KEA plus KEB plus KEC plus KED the sigma KE, right? And then we have the common denominator, that's KEA MEA. It's going to be equal to the summation of fixed end moment at E. So now I know that my MEA is simply KEA divided by the summation of the stiffness at joint K multiplied by sigma fixed end moment at E. Okay, so that, ladies and gentlemen, here is how much we can tell how much member EA will contribute to resisting the fixed end moment. This is our distribution factor. Or DF. Okay, so now we know if we have the moment at one end, the opposite end, we have the moment equal to half of that number. Now we know that each moment will be contribute in resisting the moment equal to the ratio of the stiffness. So how I can simply say that how much each member will contribute will depends on how stiff each one is. Okay, let's say if I have a joint like this, and let's say this guy's stiffness is 2, that is 2, this is 1, this is 1. The sigma K is 6, right? And that means this member will contribute in resisting the moment equal to 2/6. This member will contribute 2/6. This member is 1/6. That member is 1/6. Correct? See how when you add them all up, it should be equal to 1. Because if you have the moment here, that is M. So the resisting moment will be 2/6 of 1/3, right? Plus 1/3 plus 1/6 plus 1/6 of the moment. So in the end, it's equal to moment M. So now we have that. We have the summation of the procedure or the process. Practically, this is actually what we do. Okay, the one before that, it's like a theoretical approach. So now you see the first is, again, we have to define the relative stiffness. We need to be able to see how each member is stiffer than the others, or or vice versa, so that we know how much each member will contribute in resisting the moment. Once we know the relative stiffness, we can determine the distribution factor of each member that forms a joint. We can calculate fixed end moment next by locking the joint, right? Then once we have the fixed end moment, now you can calculate the unbalanced moment. It's going to come in and balance the moment that comes out when you unlock the joint by using this distribution factor. By using this. Okay, actually it's this. I already unbalanced moment coming out of the joint, and you can determine the resisting moment by using the distribution factor. Okay, that's more like it. Okay, and once you know the resisting moment that occurs here, you know that a half will be carried to the opposite end. Okay, and then that's the end. And now you look for more if the whole thing becomes unbalanced, because you have some issues, which I think it's better that you see the examples and try to explain it here. Okay, so that is the end of the new method. Sounds pretty simple, and it happens every year that when you look at or when you listen to the explanation, it's pretty difficult to grasp the idea or to visualize what's going to happen. So there is no better way to look at the example in the next session, I suppose. So you want to have a break now? Do you have any question? Maybe? No. That it was